Hello there guys. So today we're going to be taking a look at the following question, which is from the 2019 IMO, and it's question number N1, which reads as follows. Find all pairs mn of positive integers satisfying the equation 2 to the power of n minus 1 times 2 to the power of n minus 2, so on, all the way up to 2 to the power of n minus 2 to the power of n minus 1 equals m factorial. So let's get straight into it. The first step was to take this block of things and put it into a product. So what does that look like? Well, we can have the product of, and well, what we can do is we can say that it's 2 to the power of n minus 2 to the power of k. And we can run k from 0 all the way to n minus 1. And this equals m factorial. Okay, so now what I did was, this step did take me a while to kind of figure out. But usually with these kind of questions, you want to compare factors of both sides. So maybe you want to compare factors of 2 on the left side and factors of 2 on the right side, you know. But the kind of trick here is to compare the highest power of 2 on the left side and on the right side. So how can we do that? Well, what we can do is a mini trick on this left side. So I was just playing around with it, and what I figured was that we can factorize. So let me just write the product here. We can factorize a 2 to the k out of that left side. And what we get is 2 to the n minus k minus 1. All of this equal to m factorial. Okay, now obviously since this is a product, we can kind of split this even further, and we can say, well, it's this times 2 to the k, and then times another product times whatever's remaining. Okay, so this bit here. And this is going to be equal to m factorial. Okay, so now what do we have? Well, this left side, let's just kind of take out and analyze here. This is pretty much going to be 2 to the 1 times 2 to the 2 times 2 to the 3, all the way up to 2 to the n minus 1, which is the same as 2 to the power of 1 plus 2 plus 3, all the way to n minus 1. Sorry, plus n minus 1. Which is the same as 2 to the power of n minus 1 times n minus 1 plus 1, all divided by 2. Which is 2 to the power of n times n minus 1 divided by 2. Okay, awesome. So now what do we have here? So what we have is we can write this now as 2 to the power of n times n minus 1 over 2 times the product running from k0 up to n minus 1 of 2 to the n minus k minus 1, and that is equal to m factorial. Now, some important things to notice is this product here, it doesn't have a factor of 2. This number here is definitely odd. Okay, so it's definitely odd. So now what does that mean? Well, that means that this is the only factor of 2 that it has, or only factor of a power of 2. Okay, let's say. And this is the highest power of 2 that this function divides. Okay, so that's pretty good information, because what that tells us is if this is to equal m factorial, well, the highest power of 2 which divides m factorial has to be this. Okay, so guys, now I would like to introduce you guys to this special formula known as Legendre's formula, which looks like this. So v sub p of m factorial is equal to the summation from I equals 1 to infinity of the floor function of m divided by p to the power of I. Okay. Now what this tells us is it gives the exponent, the exponent of the largest power of p that divides m factorial. Okay, so it's quite simple. It gives the exponent of the largest power of p that divides m factorial. Now, you guys probably have made the connection already. Well, if I put a p, if I replace the p with a 2, that means that should technically be equal to this, because that is the largest power of 2 that divides m factorial. So let's go ahead and do that. v2 of m factorial, where now this m is the same as this m here, is going to be equal to the summation from I equals 1 to infinity of the floor of m divided by 2 to the power of I. Okay, so now what we're going to do with that information is form some sort of a bound for n times n minus 1 over 2. Because we know at this point that v2 of m factorial is equal to n times n minus 1 over 2. Well, we know that this is less than the same summation, but without the floor function. Okay, so if you just remove that floor, we should get this inequality. And what that means is this should be equal to, well, we can take the m out and look at the summation like this. And now this is just a standard geometric summation, which is just equal to the first term, all divided by 1 minus the first term, which is just equal to m. So we know that v sub 2 of m factorial is less than m, which means n times n minus 1 over 2 is less than m. N times n minus 1 over 2 factorial has to be less than m factorial if they are positive integers. Okay, so we've come a long way now, and we've got a bunch of inequalities and stuff going on here, which is pretty cool. Now, what I'm going to do is I'm going to let this thing here, just this thing here, I'm going to let it equal to, what shall we say? Let's say it's L sub n, okay? L sub n. Okay, so we know that m factorial is what? Well, that is equal to L sub n. So that tells us that this thing is less than L sub n. Okay, so that thing factorial is less than L sub n, which is great. Okay, so now we're gonna see if we can form a few more inequalities from this here. So what do we have? Well, L sub n, we know is equal to this. 1 minus 2 all the way to 2 to the n minus 2 to the n minus 1. Okay, so now what can we do with this? Well, what we can do is to form an inequality here, instead of kind of subtracting stuff from each term, we can just leave it as it is, right? So it should be less than 2 to the power of n times 2 to the power of n all the way to 2 to the power of n. And imagine we're doing that n times. Okay, imagine this is done n times. Okay, so it's definitely going to be less. Ln is definitely going to be less than this right-hand side, which is the same as 2 to the power of n to the power of n, which is 2 to the power of n squared. Okay, so L sub of n is less than 2 to the power of n squared. And now L to the power sub n is m factorial, which is less than 2 to the power of n squared. And now if we kind of put this inequality beside this here, what we have is we do it in red, okay, n times n minus 1 over 2 factorial is less than m factorial, which is less than 2 to the power of n squared. Now if we take this side and combine it, we have this factorial is less than 2 to the power of n squared. Okay, so now we have this random inequality that kind of comes into our hand. And we're left wondering, well, is this true? Is this inequality correct? Okay, let's check it out. And, just for time purposes, I'm going to tell you that it works for 1, 2, 3, and 4. And it's very easy to verify it because, 1 is less than 2 for 1. 1 is less than 2 to the power of 4 for the second, for 2. I'm just putting in n is 2 into here. If I put in n is 3, well, I get 6, which is less than 2 to the power of 9, for sure. If I put in 4, I get 6 factorial is less than 2 to the power of 16. And this is also pretty easy to verify. Okay, so now if I put in 5, I get 10 factorial is less than 2 to the power of 25. Okay, so now proving this is slightly more tricky. We just have to do a bit of work. So 10 factorial, well, I'm going to write 10 factorial like this. Okay, so now what I'm going to do, okay, here, is I'm going to consider the upper bound of all of these as a power of 2. Now, what I mean by that is the power of 2 that's bigger than 10 is 16, which is 2 to the power of 4. And that power of 2 bigger than 9 is, or the smallest power of 2, I should mention, that's bigger than 9, is again 16, which is 2 to the power of 4. For 8 is 2 to the 3, and then same goes all the way up to 5. Obviously 2 to the 2 is equal to 4, and then 2 squared, then we have 2, and then we can say we have 2 there. Okay, so now we know that 10 factorial is definitely less than all of these numbers multiplied together. Now, what is that equal to? Well, 10 factorial is less than 2 to the power of 26. Okay, but we can change this 2 into a 1, and that's not really going to do anything. Okay, so if we divide this thing by 2, just because we got rid of it here, we get 2 to the power of 25. Okay, so we get 10 factorial is less than 2 to the power of 25, and happy days. Okay, so this works. So now, what about 6? Okay, this is where things get a bit more interesting. We get 15 factorial is less than 2 to the power of 36. Now, is this true? Now, to figure this out, what we're going to do is a similar thing. So I'm going to write 15, 14, 13. Now, instead of considering the upper bound, I'm going to be considering the lower bound this time. Okay, so instead of the upper bound, let's consider the lower bound. What do we have here? So what I mean by the lower bound is I'm going to consider the largest power of 2 that's smaller than or equal to each of these numbers. So 15 obviously is 2 cubed. I think all the way up to 8 is going to be 2 cubed. Okay, all the way up to 4 it's 2 squared. And then it's 2, and it's 2, and then obviously it's 1. Okay, so now what does that equal to? We should have that 15 factorial is bigger than 2 to the power of 34. Okay, so now it's just below 2 to the power of 36. Now, don't worry, we can kind of work around this. And the way we can do it is, this first number here is at 8. And the second number here is at 8. So 2 cubed is 8, and 2 cubed is 8. Now, okay, so let me just rub this bit out. Now, to go from 8 to 15, we need to multiply 8 by 15 divided by 8, which is 1.875. And to go from 8 to 14, we need to multiply 8 by 14 divided by 8, which is 1.75. And to go from 8 to 13, we have to multiply that by 13 divided by 8, which is 1.625. Now, if I multiply all these numbers together, 1.875 times 1.75 times 1.625. So when I multiply these three numbers together, so this number, and this number, I get 5. Okay, so I know that 15 factorial is greater than 2 to the 34 times 5. And now we know that this number here, okay, 2 to the 34 times 5, is definitely bigger than 2 to the 36. Because 2 to the 36 is 2 to the 34 times 2. This inequality here does not hold for the number n equals 6. So what does that mean? Now we're thinking to ourselves, well, if it doesn't hold for n equals 6, does it not hold for numbers bigger than 6? Okay, so and this is actually the most ingenious part, it took me so long to figure out, but let's prove that this inequality here over 2 factorial holds for n greater than or equal to 6. Okay, let's just prove this. And the way we can do it is, well, we have 15 factorial. So this left-hand side here is the same as 15 factorial times 16, 17, all the way up to n times n minus 1 over 2. And now we know that this is bigger than 2 to the power of 36 times... now, what I'm going to do is I'm going to say, well, we know that it's bigger than all of this remaining stuff. I'm just going to say, well, what if all these individual numbers were just 16? Well, it has to be bigger than 2 to the 36 times 16 to the power of how many ever 16s are here, which is going to be n times n minus 1 over 2 minus 15. Now, this is equal to 2 to the 36 times 2 to the 2n squared minus 2n minus 15, okay, which is equal to 2 to the 2n squared minus 2n minus 24. Now, what we can do is we can split it up like this. 2 to the n squared times 2 to the n squared minus 2n minus 24. And voila, we know that that is definitely bigger than 2 to the n squared. Okay, so now we've proven this inequality. Now, this actually violates our equation, our inequality before. Now, if I just scroll a bit up, you can see on the top here, we have the same n times n minus 1 over 2 factorial is less than 2 to the power of n squared, right here. But then in the bottom here, we have it's greater than 2 to the power of n squared. Now, what this means is that this whole kind of, equation that we have here is only valid for values of n from 1 to 5. It's completely invalid for values of n greater than or equal to 6 because of this violation here, violation of this inequality for values of n bigger than or equal to 6. So now all that's left to do is this first kind of equation that we were trying to find solutions to. We know that it's not going to hold for n bigger than 6, bigger than or equal to 6. So we only have to check the first 5 numbers. Okay, so 1 to 5. We have to check for which numbers from 1 to 5, which integers does it satisfy. So if n is 1, so L1, we know is equal to 2 to the 1 minus 1, which is 1, which is equal to 1 factorial. So your combination mn equals 1, 1 works. L sub 2 is equal to 6, which is 3 factorial. So the combination 3, 2 also works, and I've added it here. Okay, so L3, okay, is equal to, well, let's see. Well, we know that that's equal to 168. Just putting it into the equation on top. And I know that this is between 5 factorial and 6 factorial. And now I'll give you guys that L4 is 20,160, which is between 8 factorial and 7 factorial. And L5 is 9,999,360, which is between 11 factorial and 10 factorial. So the only solutions is mn equals 1, 1 and 3, 2. Thank you. And this is our final solution here. Thank you so much for watching this video, guys. See you in the next video.